Thanks, Peter. Yeah, so this paper we're looking at today is flow matching for generative modeling. It's a paper by Lippmann, Chen, Hamu, Nickel, Lei, and it's a 2023 paper from ICLR. It was top 25% notable paper and now has 600 citations. So we're going to try and find out why this paper is important and what kind of real-world applications it's being used for, how it's changed the landscape for generative modeling, for diffusion models, and the types of things you can sample using diffusion models. So let's first look at this title. So flow matching, it's inspired by score matching, which is the training objective for score-based generative modeling or diffusion models, which are known as being state-of-the-art for protein structure generation, for image generation, audio synthesis, so many different applications in generative modeling. But this is a new paradigm inspired by diffusion, but it's not. So we're going to try and find out what the differences are and why it's new. So it's built on a framework of continuous normalizing flows, allowing us to train continuous normalizing flows at scale. So the reason why diffusion models are so successful is because the training objective works at scale, because you have a denoising diffusion objective, and the denoising is what the denoised image is what you're trying to predict with the neural network. And the training objective is so simple because you just take a data point from the distribution and you add noise to it in just one step. And then you denoise it by a forward pass of a neural network in one step. And then you take a gradient with respect to the parameters, and that's the learning objective. And so this is called simulation free, when you don't need to run a simulation of an ODE, like a numerical solve, or an SDE, or if we're talking about Markov chains, you don't need to simulate a Markov chain in sequence. You just take one step and then reverse that step. Compute the error, take a gradient. That's called simulation-free approach, and that's why diffusion models are scalable. But no one knew how to do continuous normalizing flows with a simulation-free based approach. So that's the main innovation of this paper, is that it extends continuous normalizing flows to a simulation-free approach by taking inspiration from diffusion models. So what we're going to do is go from a data distribution like images to a noise, and that noise is going to be Gaussian, because it turns out that doing that, it's particularly easy to parameterize this single step that takes you to a noise image. But the difference between this and diffusion is that it opens the door to training continuous normalizing flows with non-diffusion probability paths. So instead of designing the one-step transition kernel that takes you from your data to the noised image, we're not going to design a transition kernel. What we're going to do is define a conditional vector field that will take you from one distribution to another between pairs of points. So in particular, this is interesting because we can define different paths which aren't diffusion based, which could be simpler, smoother over the time of the noising, over the number of different noise levels. They're smoother functions, so that makes them easier to learn. And that's what this idea of optimal transport is trying to get at, because an optimal transport, I'm not going to define it like mathematically, but the idea is that it's the simplest way of getting between two distributions, and it involves straight line paths of this vector field. So if you're going in a straight line, then you don't need to take sequential steps. You can just go there in one step. But that's in the optimal case. But we never quite reached that. And So we're going towards closer schemes that more closely approximate optimal transport, or in one sense they are optimal, like in the conditional vector fields. We'll explore what that means. So these paths are more efficient than diffusion paths, provide faster training and sampling. So that's great, because diffusion models take a while to train, billions of epochs, right? And the loss is still decreasing. So if you can decrease the number of training steps, that's good. And sampling, that means inference time is going to be faster to generate these things, which is important in practical application as well. Better generalization. So what they got here in the abstract, they've got flow matching on ImageNet leads to consistently better performance compared to diffusion-based methods in terms of both likelihood of the samples and the sample quality in terms of FID score. And it allows fast and reliable sample generation using off-the-shelf numerical ODE solvers, which is another thing about this paper, is that doing away with stochastic solvers or SDEs. So to understand the paper, as Peter said, you don't need to know stochastic calculus. You don't need to use stochastic solvers, and there's a whole array of off-the-shelf options for numerical ODE solvers. So you can just start to explore that much more quickly, maybe iterate on your generative models and get better, reliable samples by kind of opening up that avenue of the design space. Cool. So I chose to read this paper because flow matching, like diffusion, is useful for a range of applications. In particular, you've got image movie generation, trajectories of cell genetics data in response to treatment, for example, a drug, protein design, going from the sequences of amino acids, which is genetic code for proteins, which are molecules in your body. And these amino acids, there's about 20 of them. They can be represented by tokens. And then what AlphaFold 2, the problem it solves is that it's really easy to collect data of genetic sequence. So there's billions of genetic sequences which are known for each proteins, but it's really difficult to measure data of proteins. And so there's only on the order of like 1 million known protein structures. That's the 3D coordinates of the atoms. So although we can represent the proteins in genetic code really easily, physically, in the real world, they're represented by atomic coordinates. And so the problem that AlphaFold 2 and possibly why it won the Nobel Prize was that given that there's so much more sequence data than protein structure data, can we convert all of this sequence data to protein structure data? And interestingly, going from AlphaFold 2 to AlphaFold 3, what you've got is they've replaced the structural generation module in that system with a diffusion generative model. So we've got a question. So Alex,
I was just going to make a comment that Google DeepMind has just released GenCast, I think, the other week, which is another application, very interesting application of diffusion models.
Is this a weather model?
Yeah, and I think what's particularly interesting about it is that they're using diffusion to actually simulate ensemble weather forecasting.
Yeah, so it's like medium range weather forecasting. And is it the same one that was extending the possibilities of accurate weather forecasting from 7 days to 10 days? So now you can get an accurate 10-day forecast.
I think, well, the paper claims that it's competitive up to 15 days with the most accurate weather forecasting models that use differential equations, and
which is amazing, right?
Yeah.
Like this is a model that maybe it does in some way, but definitely less reliant on differential equations. Like physics first principles based modeling is a way, and it's being replaced by just lots and lots of data of weather systems.
Well, I think it went back and forth a bit because there was GraphCast, which was using a graph neural network, and which was not, it didn't include any physics bias, but then they they had GCN, what was it, GCN, can't remember, where they put physics back in. But then the most recent one last week, they took it back out, but they're using a diffusion model. And what seemed particularly interesting to me was that they were using diffusion to do ensemble weather forecasting.
Yeah.
And so the diffusion's really important there because it's doing ensemble weather forecasting. And it
ensemble in the sense that it's modeling a distribution. So you can take different samples of what could possibly occur.
Yeah, this is very important because the weather system is chaotic.
Yeah. Yeah, because, okay, so a small change in initial conditions leads to a large change as you roll out the time.
Yeah, there's a good video on this if anyone's interested in ensemble weather forecasting by Dame Julia Slingo. She was at the Turing, I think it's at the Turing Institute a couple of years ago. You can find it quickly online. And she gives an overview of ensemble weather forecasting. But it was a very interesting application that diffusion models can compute this.
Well, presumably the reason why it's important to do ensemble is because like a small change in initial conditions leads to a large change in the weather. So therefore, if you're not interested in the average, like weather systems, so you need to take multiple samples, propagate them, and calculate the risk, like the chance that I need to take my umbrella outdoors in 10 days.
Exactly, and that was the problem with GraphCast, that it was producing results that were kind of averaged and it didn't replicate they were too smooth. They didn't have a good they didn't replicate the detail.
Yeah, well, that's interesting. So yeah, back to flow models. I don't think it does away with this ensemble thing. You're still modeling distributions. You're just not doing it, sampling it stochastically. So there could be a chance that flow models become state of the art for weather generation, for video generation. We'll go on to that. So yeah, it's having this large impact in applications. Maybe I'll just go through that now. So this is a paper. Hopefully you can see this. Yeah, MovieGen media foundation models, and it's from Meta AI, and it actually uses flow matching. This paper that we're covering now, it says here the model trained with flow matching. Yields high quality generative models for video audio. And they found it was better than diffusion models. And this is interesting. They found this is the case because you can get more explicit control over where your distribution starts and where it ends. And more importantly, where it starts when generating. You can guarantee with flow matching that you start from a normal 0-1 distribution, so that you don't induce any distribution error from when you're going to start. You're going from noise to data. Where you start is noise, and that's where you're meant to start. And empirically, they found that with flow models, you don't have that distribution error at the initial condition, the noise, whereas with diffusion models, we know you do. And empirically, that seems to be important for video generation. I don't know why that's the case, and I don't think there's any theory there. And there's been talk about the Christmas advert for Coca-Cola. It's been generated by video. You'll start to see a lot more AI-generated content. So the high-level problem is that with diffusion, we're going from this noise to data when we're doing the generative modeling, and that was with an SDE. But in this original paper from Yang Song and co-authors, they made the realization that there's an equivalent ODE that has equivalent time marginals, same marginal probability densities as the SDE that's used to generate diffusion processes. And it looks like this. Here you can see the score of the diffusion. So that's like the noise that we added. And that is a choice of the forward SDE. And so what you're doing is going to do score matching, denoising score matching to regress this to estimate that, and then simulate this back in reverse time. And we can use an ODE to do that. It's kind of up for debate, I think. Some people say that ODEs are just better than SDEs. You should never use an SDE. I don't think that's the case, because with this paper from NVIDIA, Karas et al., you can see that they've done an experiment on this, and they found that some level of stochasticity to be useful. If I can find, yeah, so this is like, the red line is like the ODE simulation, and everything else is some kind of level of randomness, churn in this Langevin dynamics. And so there's like some minimum that corresponds to, you want some level of correction from the Langevin dynamics, which is going to just jumble up the particles a little bit and correct for some numerical simulation error. Whereas the authors of the flow paper, they're claiming that you should always, maybe they're not claiming this, but kind of folklore is that you should use ODEs because they're more efficient numerical solvers. Well, actually, it might be the case that the real gain is coming from the choice of paths, choice of diffusion paths, and not whether you use an SD or an ODE. But this paper has opened up the design space of the diffusion paths to non-diffusion probability paths. And how does it do that? It is, instead of doing score matching, we're going to do flow matching. So now to introduce some of the notation. So you've got X, which is, you can think of as a data point along the flow path or the noising path, and X1 is a data point drawn from the data set, the data distribution Q, which is our distribution of images, and U is a flow or a vector field, which describes the dynamics of that ODE that I just pointed out in the score-based generative modeling paper. We're going to do away with this, simplify it, don't need to define a score, just need to collect these terms and define a vector field. And that vector field is U. So it then looks like it then looks like this. So that's the ODE that you're trying to solve. And we want to learn this, which is equivalent to is going to be defined as RU, which is the vector field that we're trying to learn. And so people have done like a lot of work to reduce the number of steps of diffusion models. And one way of doing that is to explore different diffusion paths. And like I said, whilst it could be the case to convert the diffusion into ODE is more efficient to integrate in an SDE, some stochasticity could be beneficial. But by modeling an ODE directly, we can help explore the design space of these deterministic sampling processes. And there's a larger space of these vector fields to explore than being restricted just to diffusion paths. And so we can also explore second-order solvers that seem to offer better computational trade-off for flow models. And so how does it work? You've got marginal vector field, which is U, which is the thing that's going to guide our samples. And that's what we want to learn. And this, what we want to learn on the left-hand side, is equivalent to this on the right-hand side, which is an integration over the data set Q over conditional vector fields, U of X conditioned on the sample from the data set. So what this is saying is that we can average over conditional vector fields to get the thing we need to take samples of. And then what that implies is that this objective that we were going to use to learn this vector field, which is flow matching, which is inspired by score matching, but just bunging everything together of the reverse OD into one term, which is U. So this is flow matching, but we don't know this term actually, but because of this, that the term that we want is the average over the data set of this conditional term, which we do have, then you can use this objective, which is the same as the original loss, up to a constant that doesn't depend on theta. So when you take gradients with respect to theta, you get the same gradients. You can use it to learn. Okay, so this is the same math that was used for denoising score matching, and it's the reason why diffusion models are scalable, because they're simulation free. Now, instead of using marginal scores, denoising, we are now doing something more general, which is using conditional flows and not conditional scores, which expands the design space. And so what problem does that help you solve? Well, you've got, what's nice about flows is that you can go from any starting distribution to any final distribution, which is not the case for diffusion. With diffusion, you need to go from a pure noise distribution to any final distribution. So you have restricted on your choice of starting distribution. And it's useful because we can use it in these 2D examples, but also for images, for videos, for proteins. Okay, so how does this, one of the nice things about this paper is that it relates it to diffusion explicitly. So it says how it generalizes diffusion. And it does this by looking at what this conditional vector field looks like for a diffusion path. So the diffusion path is defined by this transition kernel. You're adding noise to your data with this normal distribution conditioned on your data point. And then plugging into the equations and turning the handle, what you get is this conditional vector field, which is the thing you use to regress. Now, for this particular parameterization, or this choice of forward diffusion, the variance exploding path, flow matching and score matching are equivalent, because you can see here, x minus x1, well, x1 is the sample from the data distribution, and x is the sample from the data distribution plus noise. So x minus x1 must be noise. So when you plug that into the objective up here, you see that V, which is your neural network, and U, for variance exploding flows is just noise. So the neural network is predicting noise. So therefore, flow matching and denoising diffusion are equivalent for variance exploding SDE. However, that's not the case for variance preserving SDE. So you can see here that you've got alpha 1 minus t, which is just a parameter of the forward noising path, pre-multiplied by x, which is the noised data point that's sampled from this one-step transition to noise the data, subtract the original data point. Now, if you subtract x1 from alpha 1 minus t x, well, that's going to be alpha 1 minus t squared x1 plus alpha 1 minus t noise minus x1. You don't get noise. This thing in the brackets, unlike the variance exploding, isn't noise. You're not predicting noise anymore, so it's not denoising diffusion. Something more general than that. And in the experiments, what they found was this new target, this new loss, is more efficient for training and for inference. So maybe that's a good point to go into the experiments of the paper. So there's two main experiments, one for training time and one for efficient sampling. And this is the training time. So the idea is that the target that you're trying to predicting the neural network in this regression, in the learning objective, is smoother. So it reduces variance in that stochastic objective. And so you can do faster training. And you can see with this flow matching with diffusion, with score matching diffusion, it's slower to train than flow matching with the diffusion on the variance preserving SDE. And now there's an even faster path that they propose, which is not a diffusion. So we've got a comment here. So this has to drop, no problem. Yeah, so what's this other path that they propose? This one is optimal transport path, which is not variance exploding or variance preserving. It's just a straight line. So the high level approach is just to directly learn the vector field instead of the added noise. And so the design space is increased, and we can make the path straighter and integrate in fewer steps. So what you want to do is take your data point and do an optimal transport between your data point and a normal 0-1 Gaussian. And that allows you to get straight line conditional paths. And it's interesting because we can choose which paths that we take, and we can choose ones that are more efficient. Whereas the variance preserving diffusion, you have curved paths which take more steps to go from noise to data to integrate. These optimal transport paths take less steps, and so as well as leading to faster training, so reduced FID score for number of training steps, it also leads to faster inference. So and we're using ordinary differential equations, so they're using adaptive solvers, which you can tune the numerical error induced by solving the ODE by using these things. And we can also explore the number of steps and the error in solving the ODE. So this optimal transport path, the straighter lines, it induces smaller error for a given number of steps in generating. And not only that, is that you get smaller FID than this diffusion path with flow matching.
So that I might have completely misunderstood. So you train the model to predict the vector field, and then you use the ODE solver to actually trace it out, right?
Yeah, that's right. Yeah.
Okay, thank you.
Does that mean that at inference time the paths aren't straight if you're using optimal transport?
So these paths are straight lines between these conditional distributions. So it's only the optimal transport between two conditional Gaussians. But at inference time, the paths are not straight because at inference time, you're using the not conditional vector field, but the marginal vector field to solve the ODE. And so although it was optimal for in the training, the conditional vector field, it's not optimal in the marginal vector field. So the paths are not straight at inference time. But that would be the goal. Like optimally, you'd want the paths to be as straight as you can. But that's not true in practice. Does that make sense? I feel like I can explain that better.
And you still
No,
have
that makes sense. I was just thinking it because, like, if it's straight at inference time, you don't really need an ODE. You just keep moving forward, right?
That's right. If it's straight at inference time, you just take one step and that's it.
And at inference time, you call the model several times to essentially update the flow profile at several steps as you move forward in this ODE solving.
Yeah, that's right. Yeah.
Thank you.
So inference time, the paths are definitely not straight, but in the training algorithm, the conditional paths are straight, and now that doesn't imply that the inference time paths are straight.
Yeah, and so you probably could also tune your compute a little bit up and down, well, depending on how often you recompute the flow field along your trajectory, right?
You can tune what?
Say if you solve if you have your ODE solver, you can sort of tell it how far ahead it should solve to, right?
Yeah.
If you make this step smaller, it has to call the model more often to update its flow rate, right? But you likely get better outputs, no?
Yeah, that's right. I think so. In these higher order numerical solvers, the way they work is they do like they try and look forwards, do like a local expansion that makes it more accurate, and then compare that to so a lower order solver, and for that you get the error, and using that error, then you can adapt how far you move forward at each step and get closer to like optimal step sizes. So yeah, that's the idea behind adaptive solvers, and using ODEs makes that possible. So I suppose that's not specific to flows, but ODEs, yeah.
Oh, very cool.
Yeah. Yeah, so then you've got the numerical results, and I think what this is saying is that for like the same network, the same architecture, you're getting lower FID scores using these types of paths that are generated by flow matching rather than diffusion, and the training is more efficient, so you're able to reach lower FIDs given the same number of same number of training steps. So the numbers are better, but I think the real proof is in the pudding of the number of applications that are coming out with flow modeling for, like, for example, videos, and not only improvement in sample quality, but the types of problems that you're able to solve have expanded. So with diffusion, you have to go to pure noise, whereas with flows, although it's not explored in this paper, you don't have to go to pure noise. You can go from any one distribution to any other distribution. And I think that's useful for papers like this, if you want to read into that, if you're treating cell dynamics or patient dynamics for medical treatment, because you can imagine there's a population data set of cells that have been untreated and cells that are treated, or patients that have been treated or haven't. And so that's not going from noise to data, that's going from one population to another population. And other applications include this discrete flow matching, which is trying to explore if it's possible not to do autoregressive generation using LLMs, but generation which is non-autoregressive. So instead of sampling one token at a time, you can use the model to sample multiple tokens at a time. So this is just one of the papers that are attempting that, but they've decided to use this flow matching framework. Cool. So I think that's everything. If we want to have more discussion, what's this?
Hi, I had a question about the equation 9. Is there a reason why the learned vector field is not conditioned an x1?
The learned vector field over here.
Yeah, equation 9, because it's not conditioned on x1. I was wondering why that is.
So this learned vector field, it should be. think it would be possibly clearer in notation if this, unless I'm misunderstanding it. I think V is like the neural network, and you parameterize it by theta, and you also feed into the neural network the data x1. No, you don't. No, because you won't know that at inference time. So that's the thing, right? So you want, when you're denoising, you don't know what the denoise data point is. You just have the noise data point, and your vector V will take you in the direction of the trajectory. So you don't want to be conditioning on something that you don't have at inference time.
So I think the dependence on x1 comes through the probability PTX of x1 on the left there.
Yeah.
So it's not. So and actually, this sort of struck me about this equation as well, and I wasn't going to raise it because I wasn't sure it was that interesting. But yeah, I also saw that just notationally that seemed to be a lack of symmetry between those two expressions inside the brackets there. That VT doesn't depend on x1, but the whole equation does, because you're sampling from a conditional distribution, conditional x1.
Yeah.
But I don't know if that's like, is that an interesting feature about that equation, the fact that VT does not depend on x1? Or is that not that interesting?
I think it's similar to conditional score matching or denoising score matching. So there's nothing that really changes apart from the fact that instead of a score, it's a vector field. So the idea is that you know the conditional score or the conditional vector field, and you're using this to compare it to the output of your neural network. And so then that's your it's like, imagine you're taking a flight, okay, from London to Tokyo, and there's the plane, and you're trying to estimate what direction you should go in, what direction the plane is going in, and so that's what V is, and that's parameterized by theta, and so it's this is the neural network. And so then once you've learned it using this loss, which is evaluated with stochastic gradient descent, or trained using stochastic gradient descent, then once you've learned that, then you can use V without any knowledge of x1 or the distribution of x1 to generate new samples. But yeah, this is very similar in conception to denoising score matching.
One thing I was wondering, more of a general question that I don't think is addressed in the paper because it's not the point, but like, I think what this paper, the whole thing the paper is saying is like, we open this up so you don't have to have, like, as you said, pure noise as the distribution that you're going from. And then also you don't have to use diffusion to generate your probability path. You can use other equations. And then my question is like, will we ever, like, is there a reason that we want to not use pure noise as the initial distribution? Like, will we ever move away from that? And then, like, is it, it seems like this optimal transport objective is better because of because it creates straight lines, or I guess it creates more direct paths. But are we gonna explore anything besides optimal transport? Like, this paper is opening up the field in a way, but it's like, is that something we would really want to explore? Is that an area that could lead to a lot of improvement?
Yeah, it's a good question. And I think on an application side, yes, you do want to explore when you're not signing from pure noise. With that example of the cell populations, and they have the data X is like maybe genetic expressions of the cell, and then you will treat a cell with an environmental change or drug treatment, and then the cell's genetics X will change. So that's before treatment and after treatment. So then you can kind of learn the dynamics going between those two distributions, and and that's not a denoising, but that's just more kind of studying what happens to biology. And I think understanding like biological and lived systems is one application. And then in terms of using different paths and exploring the space of different paths, while this is like conditional optimal transport in that these lines, they are straight, this paper isn't saying that they have found the optimal trajectories. So that's a problem that is not simulation free, although I believe that there are some papers that explore how to learn these optimal trajectories, but they always seem to require solving an ODE in order to evaluate the loss, and then doing that iteratively in an algorithm that's related to expectation maximization or the Sinkhorn algorithm, and that is just hugely expensive and it doesn't scale. So the question is, how far can we push simulation-free algorithms by exploring their design space, and how far does that get us in terms of sample efficiency, in terms of like making the inference time smaller, and pretty far, right? So it's like you can sample videos in a few seconds, but these videos are short; they're like only 2 seconds long. And you can tell that from watching the Coca-Cola advert, because each frame, each scene is only about 2 seconds. And so it's like, how far can we push this design space and this framework? Would be is the type of question that is sort of trying to be answered by looking at these paths and making them better.
And would the Coca-Cola advert is only 2 seconds per scene, and that means that there's like a dimensionality issue here. Like if the data you're creating is too high dimensional, it just like the quality degrades. Is that it? And like maybe, yeah.
Let me think. So yeah, so if you increase the number of seconds, then you must be increasing the dimension of this thing X. Because I think how these things work is that it's like predicting all of the video at once, with like a video transformer as the flow network or the diffusion network, and increasing the amount of time that the video is generated increases the size of X, the number of dimensions. I'm not sure what the bottleneck is. It's a good question, because it could be the bottleneck is like compute. Like you need just bigger GPUs to make the dimension bigger.
That's the case, I bet we'll see a lot of papers on like how to maybe do like to share things, to share diffusion processes across GPUs, or like flow matching processes across GPUs.
Yeah. I mean, this paper has so many authors. It's the whole movie gen team at Meta that I wouldn't be surprised that like the bulk of the work is that kind of thing.
Yeah. One other, I think that's a really interesting point that you brought up before about like, so, you know, transformers are general sequence to sequence models, and it sounds like flow matching models could be like general distribution to distribution models. So that's like and so you could go from like one real world distribution to another. I think that's a really interesting, I think that's a really interesting space to think about, like what problems maybe we could find there, besides the ones that we're using it for already.
Yeah, agreed. Hey, Anna, did you have a question?
Yeah, so I had a question about the equation 9. So I'm a bit confused. Why is it conditioned specifically on x1 and not on xi? Is there something special about x1?
Why is it conditioned on x1 and not on xi?
Yeah.
X X1 is the sample from the data distribution. It's a good question.
How they choose X1, is that some sort of reference point?
Yeah, exactly. It's the reference point from the data set. So if you have a data set of images, it's like one of those images.
Is there any particular way how they choose the reference point, or is that a random?
Just uniformly, like they just sample them uniformly from the data set and take an so this expectation is like integrating over the whole data set of samples. But in practice, you're computing this expectation with a mini batch. And so you'll take like maybe 64 samples from the distribution, 64 images from Q, and evaluate an approximation to this expectation. And you're saying that mini batch is evaluating this for the whole data set. But what you don't want to do is to evaluate it over the whole data set, because that means that your training expense is proportional to the data set size. And because we want to scale this to large data sets, we can't have that. So you need to have a training objectives that's independent of the data size, of the dimensionality of the data as well. And so you evaluate it approximately via mini batch. So you're going to take a batch of samples from Q and evaluate this with a Monte Carlo estimate of this expectation. Then you can take a gradient with respect to that Monte Carlo estimate. But yes, X1 is just sampled uniformly from the data set. It's a good question. So Arvid, did you have a question?
Yes. So could you explain again how the U of T is calculated, and how is T chosen? Is T is also sampled, right?
Yeah, that's a really good question. I didn't explain this because the details are quite complicated. So T is sampled from a uniform distribution, and this is the simplest way to evaluate this. But actually, T it doesn't have to be uniformly sampled because if you evaluate a different distribution of T, you would just get some kind of importance sampling, and that importance sampling you evaluate with respect to a different distribution, and you get a weight, which is the reweighting of those two distributions, and that comes out as a constant out the front of this objective, and that is called likelihood weighting. Now, in the design of diffusion models, you can use different options for this likelihood weighting that all produce different quality of samples. So that's something you could explore in the design space. And how do you evaluate U? I mentioned that the marginal UT of X, you can't evaluate, we don't know it. But the conditional, you do know, because you know your source distribution is Gaussian. And that just makes this easy to compute. And so you can go through these equations. Theorem 3 will have a derivation, and you can see how they're going to compute this.
And that is it also so this is calculated in one single step?
That's right, yeah.
And but it also relies on the fact that you made the assumption of Gaussianity in the final distribution, or in the kernel you sort of apply at each time step, right?
Yeah, this is the assumption. So let the conditional of the kernel be a Gaussian probability path, as in equation 10. Yeah.
All right, I have to read it. It's...
I'm now just thinking, why does this mean that it's not a diffusion necessarily? Because diffusion also defines this.
Yeah, exactly. It sounds just, but because it's Gaussian, right? We can do this. We have this equivalence between the ODE and the stochastic process, right? But that
Yeah.
only works in this very specific case, no?
Well, I think that if you define an ODE or an SDE, which is a diffusion, then that is enough to specify what mu and sigma are.
Yeah.
But in training, you're only interested in what mu and sigma are. Actually, you don't care about what the ODE or SDE that was used to parameterize mu and sigma are in training. So they're saying just, we don't care about ODE or SDE. Just parameterize the mean and standard deviation of this transition kernel. And in that way, you can use non-diffusion paths, and you can say that at time 1, mu is 0 and sigma is 1, so that you're guaranteed to start at the normal distribution. And do kinds of things like that. And so you're now no longer interested in ODEs or SDEs. You can just directly parameterize what mu and sigma are. And that means that you can evaluate this in one step. And they found a way to convert the conditional probability distribution to a conditional marginal distribution using theorem 3. So yeah, I recommend looking at the derivations of theorem 3.
Thank you.
Thanks. Okay, thanks everyone. I think we've run out of time here. So thanks for coming and thanks for listening to me.
That was a great presentation.
Thanks.
Hope
Cheers,
everyone has
guys.
a good weekend.
Thank you very much.
Bye.